Today we are moving towards section 6 related to magnetism and electromagnetism over there, in which the subtopic which I am going to complete today is related to magnets and magnetic field over there. So, according to examination point of view, I will say here, do the past papers and when the syllabus is complete, go for topicals and try to complete your preparation. And overall revision is the key to get the complete overview of the topics into your mind over there. I think magnetism is an attractive subject and but don't get repelled by the exam. Revise it again and again, okay? Okay, let's move towards magnets produce the magnetic fields over there. First of all, I will say here, magnets produce magnetic fields around it. Produce magnetic field. Magnetic field over there. And all magnets have two poles. One pole is called North Pole, and the other one is called South Pole over there. And a magnetic field is a region around where magnetic materials can experience a force over there. For example, I take here a magnet bar in which I say that there is a North Pole and there is a South Pole over there. Magnetic field lines will originate from North Pole and end up on South Pole over there. And these magnetic field lines never cross each other. They never cross each other. And these magnetic field lines, we can say, are occupying a region around it, which we can say is a region which can experience a force of attraction or repulsion by any other, it is going to end up like South Pole always will be directed towards South Pole over there. So North Pole and South Poles are present. Magnetic field lines are used to show the size of direction of magnetic fields. They always point where North and South is going to mentioned over there. So this is your North Pole and this is your South Pole. And the lines which I have drawn, those are called magnetic field lines over there. And if I talk about placing the north and south pole of two permanent magnets, bar magnet near each other, then I will say here north and north, south and south poles repel each other, means same poles repel each other. They have repulsive force. On the other end, if I say north and south or south and north, they show the force of attraction between them. They show the force of attraction between them. And magnetic field patterns can be seen using a magnetic compass over there. For example, I take here a magnetic compass to show you how magnetic field lines are going to draw the magnetic field over there. Then I am simply saying here, for example, this is a magnet or permanent magnet bar over there. And you are placing a magnetic bar according to north and south pole. What will happen? It will show its north towards this direction, north in this direction. It is going to show north in this direction and south in this direction over there. It means then I will join the magnetic compass for the next case over there also. And it is going to be taken from here. If I place a magnetic compass at this point, it is again showing the North Pole and South Pole. Then it will be south towards north and it is going to be taken and this field is going to draw around a magnetic field around it. So the magnetic compass is going to help, and if I mark all of these points in the form of North Pole direction over there, then I will simply say here, I can draw a magnetic field line around the magnet which is originating from North Pole and ending up on a South Pole over there. So compass and iron flings align themselves with the magnetic field over there. And you can use the multiple compasses to see the magnetic field line coming out from the bar magnet between the bar of two bar magnets over there. So magnetic field patterns can be seen using magnetic compass. So magnetic field line field patterns can be observed by using magnetic compasses, like as I have drawn for you, by using magnetic compasses over there. So this is the way how to go with it. After that, I can also say magnetism can be induced in any magnetic material over there. So magnetism can be induced over there. Magnetism can be induced. How magnetism can be induced? I will simply say here, magnets affect magnetic materials and other magnets over there. Like if I take a permanent magnet bar and I take some magnetic material near it, I can say I'm taking a small nail of iron to be placed near it. And this iron nail will induce some magnetic effect over it. And you can use over there, like poles repel each other and opposite poles attract each other, and both poles attract the magnetic materials. Even though you are placing it near the North Pole or you are placing it near the South Pole, both are going to, both poles attract magnetic materials. And when magnetic materials brought near to the magnet into a magnetic field, the material acts as magnet, and this magnetism has been induced by original magnet. So here this iron nail will also be magnetized because of this permanent magnet bar over there. And this induction of magnetism into magnetic material, as it will be closer to the magnet and the magnetic material get the stronger induced magnetization or magnetism will be over there. So if I place it this nail near bar, near magnetic bar over there, strongly magnetized, and if I place very far from the bar, then that will be weakly magnetized over there. This is the induction of magnetic material due to permanent magnetic bar over there. On the other end, if I move towards, now I will have to move towards electromagnet over there. Electromagnetism, I will say here, I will have to move towards electromagnetism. 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 So this is the subtopic again, about which I will say here that electromagnetism means the induction of, we can say, electricity, magnetism, because of the effect of, we can say, uh, electromagnetism is like when a current carrying wire is being induced with the help of magnetic field over there or electric field passing through a point, and electric current is passing through anywhere, then we can say it can induce over there that we will have to say when electric field is passing through and electric field is passing through magnetic field over there, or we can say when electric current is passing through a wire, then magnetic field will be induced through it, which can be taken in the form of right hand grip rule over there. Let's move towards electromagnetism, which I am saying here. When a current carrying wire, when a current carrying wire is grasped in a right hand and if erected thumb indicates the direction of current, then curly fingers will show direction of magnetic field. This is also called right hand grip rule. Right hand rule. Okay. Show the direction of magnetic field. And if I say here, a current carrying wire creates a magnetic field, means electric current in a conductor produces magnetic field around it, then how I will show it on the figure over there. For example, this is a wire and you are holding it in your hand and current is flowing in upward direction. This is current. And when current is in upward direction, then magnetic field will be shown in this form. That is being the illustration that when current is flowing through this conductor, magnetic field will produce around it. This is called electromagnetic induction over there. The larger the electric current, the stronger the magnetic field over there. If current is larger, then magnetic field shown with the letter D over there will be strong over there. And the direction of magnetic field depends on the direction of current also. For that purpose, we will have to take a right hand grip rule over there, which I have given in the form of statement above, that when you hold this current carrying conductor in your right hand and your erected thumb show the direction of current, then curly fingers will show the direction of magnetic field around it. And the magnetic field around a straight wire, there is a magnetic field around a straight current carrying wire. The field may be in the form of conocentric circles. Like I have drawn one circle, you can draw another circle over around it. You can draw another circle around it. And the direction will always be like in this form. And these are in the form of conocentric circle over there. And the magnetic field in the center of the flat circular coil of wire is similar that of the bar magnet, and there are conocentric ellipse stretched around the circle. If magnetic field and current carrying wires are taken into flat circular coil over there. If I am taking a flat circular coil, then I say it is in the form of conocentric. But if I take around a solenoid, around a solenoid, for example, I am taking a spring-like wire. I am connecting it to, I am saying a battery. Battery like voltage, like EMF, Not, it should be shown by the symbol voltmeter like that. I have to take the battery like in this form, plus minus. I'm introducing here a switch also. And now, when the current is flowing from positive to negative terminal over there, then I am saying current is directed towards downward. And if I hold this wire in my right hand, then my erected thumb will show the north pole of the magnetic field. When we hold a current carrying solenoid in our right hand, then erected thumb will show the direction of north pole of magnetic field. Field over there. So this is the way how to move towards magnetic field around a solenoid over there. So the magnetic field inside a current carrying solenoid is a strong and uniform, and outside the coil, if I talk about here how the magnetic field will go from here, this was the current carrying solenoid, and you are saying your north pole is on this direction over there because of right hand grip rule, then magnetic field around it will be shown like in this form. This will be definitely the south pole, and magnetic field lines near the spring will be having a strong field over there, but far away when they are moving from this way like that, then this is going coming in, this is coming out. Then at the far distance, that will be very weak over there. North and south pole of bar magnet, and this is called electromagnet over there. So magnetic materials can be soft and hard, that can be easily magnetized, that is called soft magnetic material. Magnetic material, the material which can easily be magnetized is called soft magnetic material, that can be taken as iron. A magnetic material is considered soft if it loses it induced magnetism quickly, or hard at grip permanent magnet like that. So we can say soft magnetic material are those which can easily be which can be easily, which can easily magnetized when current flows through them. Through them, and that is called soft. If I take the steel wire or like such substance, with such wires or such substances which cannot be easily magnetized, they will stay permanently little bit magnetized over there on the flow of electric current for one time over there. Those are called hard magnetic materials. For example, I said the steel over there. And you can increase the strength of magnetic field around a solenoid by adding a magnetically soft iron core through the middle of the coil over there. And iron is used in transformer. Iron is used in transformer over there to increase the strength of magnetic permanent magnetic field over there. After that, in the next video, we will move towards the motor effect and electric motors and loudspeakers. I will also move towards electromagnetic induction and transformer. That will be the end of our this section. In the next video, I will go with in more details related to these electromagnetic induction and electric field to relate the magnetic field, our electric current, and Fleming's left-hand rule will also be explained in the next video. Thank you so much for today. Allah Hafiz.